I'd like to invite Arash for his present.
So, good morning, everyone. Pleasure to be here. And beautiful to see you on Enschede. We're very lucky. It has been a really sunny day. That's very common. My name is Arash Rasooli. I'm invited here to talk about research that I have done a few years ago during my PhD at Delft University of Technology. I'm currently involved in EKO Instruments. It's a company we develop measurement instruments for solar and thermal analysis. And I'm also still active in Delft University of Technology. And the title of the thesis of my PhD was In-situ Determination of Buildings' Thermo-Physical Characteristics. So you can see how perfectly it matches with the theme of this workshop. So just a quick introduction. I did this project at TU Delft. I finished in 2020. So you can imagine I don't really remember all those technical details, but if you have any question at any part, you can always contact me and I'll share the articles or the book with you. I'm currently in EKO Instruments to make thermal analysis instruments for measurements. We are still active in the field of building physics, so we use our instruments to measure parameters that are in building physics worldwide with countries all over the world. So I've also been active in TU Delft from 2012, so 13 years until now in the chair Building Energy Epidemiology. And I've also been active in RIVA and TVDL, the federations and associations for HPC in the Netherlands and in the world. So, introduction to the topic, why research important to us? This kind of research to determine building thermo-physical characteristics is important. We want to determine the building thermo-physical characteristics because it's the critical step to characterize the building's thermal performance. So examples of this are thermal behavior evaluation in the building. It's very important for energy audit, energy labeling, material construction, and quality control, making efficient renovation decisions, energy policy, and many more. So what's really important here, I cannot emphasize more, the measurements are super important. Measurements. And in my experience, I want to emphasize the importance of in-situ measurements. It's really important to make in-situ measurements because it's really different when you do in-lab measurements or you make calculations in the field. Buildings perform than what you expect or what you measure in the lab. And that's a fact. So the problem with making measurements is that for the building characteristics, sometimes the existing standard determination methods are extremely time-consuming and therefore not really practical. So, for example, for the thermal resistance and thermal transmittance evaluation, which was the main focus of my work, we have the two standards, ISO 9869 and ASTM-C 1046 and ASTM-C 1155. These are the two standard methods that are widely used in the world. So the research has shown that these methods take, in sometimes, up to 2 months of measurements. So you can imagine you leave your sensor, the system, and you have to come back in a month or weeks or 2 months later. And they're subject to many constraints. So it makes sense that some parties totally want to skip this kind of measurements and rely on other values such as calculation values or estimated values. So the aim of this research has been to develop, test, and validate new rapid feasible in-situ methods to determine some of buildings' most important thermophysical characteristics. So we looked at this at two different scopes. One is component level. So at the component level means we looked at the wall or window or door, and we try to improve the existing standard because standards are still the most important because they are accepted by everyone. So we have to invest in those. And at the other level, we start developing alternative methods other than the standard methods. Then we went to a larger scale. So system level, we explored global methods, which I will explain all of them in a bit. So at the component level, we look specifically at the walls. And there we try to look at thermal resistance, thermal conductivity, volumetric heat capacity. And these three parameters are super important because from those you can calculate many other characteristics such as thermal conductance, diffusivity, inertia, etc. At the system level, we looked at parameters like heat loss coefficient, thermal capacitance, and air exchange rates. So at the system level, it's quite different than the component level because we have to globalize things. So different researchers and different groups have different definitions of parameters based on what they want to find and what they want to reach. So to improve the existing standard method, the standard method of finding the wall's thermal transmittance and thermal resistance, the U value and R value, is to use a heat flux sensor and temperature sensors and follow the standard. So in this part, I suggested using an extra heat flux sensor in addition to the existing. And there I showed that we can reach the conclusion 6 times quicker. But still, this method takes days to finalize. So we address thermal resistance this way. The advantage of using this edition of the standard kind of extension to the standard method is that it's effortless. You don't need extra knowledge. You don't need to know new analysis. Still, it's based on the standard method, so it's still acceptable by many people. It's very straightforward and feasible. The problem is that it is still too long and it is also static, which means we cannot address the dynamic behavior of the buildings. So, therefore, we started working on new methods. So the new method that we worked on, and I will explain a bit later, is relying on the theory of thermal response factors. And this is a basic theory in heat transfer, which is very close to my heart because I've also been teaching it for 10 years at the university. So the theory suggests that if we excite one side of a wall with a triangular surface temperature pulse of 1 Kelvin, we get such heat flux profiles at excitation side and the opposite side of the wall. So this is very important. And these heat fluxes are called response factors that are in conjunction with the surface temperature pulse that is in the form of a triangle. That's very important because we use this to develop our method to determine buildings' thermo-physical characteristics. So, what did we do? We took this theory to real life. So we applied it in real life, in real walls in the Netherlands, and we studied the performance of the walls based on this method that we developed based on this. So we call this method Excitation Pulse Method, EPM, and we did a patent on it because it was a new idea, of course. With this method, compared to the previous method, which took days, we could do 25 times higher, faster of measurements. So in order of hours instead of days, we could find the thermal resistance of existing walls. So we found thermal resistance with this method. It is quick and efficient. It was accurate and precise. It was dynamic, so we could address the dynamics of the walls. And it also gave us more information than just the RC value, which I will explain a bit later. The problem, though, is that it needs special equipment to perform this method. So you need some kind of equipment to perform this kind of test. And like any other method, it has limited operation range. So what we did, we took it further. We built a prototype and we studied different aspects of this method. We defined the properties of the walls. So in each step of development, what we did, we studied the method by simulation or building physics simulation, used software console multi-physics to address the heat transfer problems. And then we also did experiments. So it was a combination of experiments, simulations, computation, everything together. That's really important when you want to do scientific work, combine different methods, experimental methods, simulation method, computational methods, and so on. So we advanced the equipment and we did some tests to study the experimental aspects such as 3D heat transfer effects, size of the heated area, properties of the pulse, and accuracy of the method. Then what we could reach with this method further by simulation, experiments, and computation was we could also find the accuracy and precision of this method. And we applied this theory of response factor in real life. We studied the performance of the method in multi-layered walls. That's always a question. So what we found is that with this method, we could even find a kind of understanding about the possible walls composition, because sometimes you have multiple layer walls and you have no idea what's inside because the wall is pretty old, maybe 100 years, maybe 800 years old. And with this method, we could kind of find the layers and the properties of what's inside. So kind of interesting. So what we used further, when we advanced the method, we used inverse modeling. And with inverse modeling, what we could find was other thermal properties with the same method. So previously, we looked at thermal resistance, and then we could find thermal conductivity and volumetric heat capacity and the thickness of the wall. So we could also address this individually. So this was at the component level, and this was where I had most interest because you look at one component, it's easier to deal with, and you can go really in depth of that. But that's not always feasible in real life. Hey, we're dealing with hundreds of thousands or millions of buildings, and we cannot go to every building and look at every component. So let's find if we can do something else to address the problems in an easier and more user-friendly way. So then we look at global characteristics. So instead of just looking at the window or a door, let's look at the whole house, the whole building. So what happens here is that we can, instead of modeling a component, we model the whole building. But we have to be careful to make a simple model because we want to use it easily. So nowadays, you know, buildings, some of the buildings are equipped with many sensors, like BMS, building management systems, the HVAC systems, especially also if you go to places like here in a university or in schools and in commercial buildings, there are many sensors installed to control the temperature, relative humidity, etc. And therefore, we can make use of this data. So what we did, we had a set of sensors, in total around 2,000 sensors, and we monitored 100 houses in the Netherlands using these sensors. And we looked at parameters like air temperature, relative humidity, CO2, motion, energy, of course, and so on. So this data normally is called onboard monitoring data. So it's data that is available already from the existing home automation system, HVAC installations, smart meters, and monitoring systems. So what we did, we used inverse modeling. Inverse modeling was a very important part. So these are examples of how you can model a building, a single building. So any heat transfer system can be analogized to an electric system. So the single house would be modeled in different ways in different electric circuits. And depending on how you want to study and what you want to achieve, you do your analogy and move forward. So what we did, we used inverse modeling in a very simple model. And then we used genetic algorithm to find some of the global characteristics of the building. So, which means we made the building, we modeled it as a series of big resistor, big capacitor, and a big ampere source. So, for example, solar radiance, that's kind of a power source. So what we looked at was heat loss coefficient, global heat capacitance, solar fraction, and air exchange rates. And again, these kind of characteristics are different in different kinds of research because with different, they come with different definitions and different purposes. And in this kind of modeling, we have to be careful because we always globalize and make a lot of assumptions in between that are not very accurate. But the advantage is that it's at the building level, so we don't talk about one component anymore. We can just talk about the whole building inside many buildings. It's less intrusive, so sometimes you are really not welcome in people's houses with your equipment to do measurements in reality. In our case, we were welcome to go to 100 houses, but that was just by luck. Then it comes at a lower cost because your data comes mostly from the existing sensors or very cheap sensors. It's not a lot of equipment. It's also less hassle. So you just collect the data and do the analysis. You really rely on analysis rather than just the sensor. But of course, let's accept the less accuracy in this level. So to finalize, many people, because I addressed different methods and different aspects of measurements, many people ask which method. So what we could find, there are many conclusions of the research, but what we found is that in-situ measurements are absolutely crucial. So in one case, we found 400 overestimation of the thermal transmittance that we could resolve by doing the measurements by our own EPM method. So the choice of method, now if you ask me after all these explanations, different methods, different techniques, what is the best? There is no answer. It really depends on what you want to study, what you have at hand, and what you can afford. So based on target and circumstances, you can find the right choice of method. So for example, if you have, if you're in summer or winter period, if you have large temperature gradient and you have standard equipment and you're welcoming people's houses, I really invite everyone to use the ISO 9669 extension, which is scientifically not the best method, but it's globally accepted. So that's very important because it makes it acceptable and it makes it welcome. Then if we don't have that and we have low temperature gradients and we have access to advanced instrumentation, we could suggest to use the EPM method. Patent is released and everybody can use it. We need to make a prototype and some advanced equipment and take the method further. And finally, if you're not welcome in people's houses, if you cannot afford doing that kind of in-depth study in every component level, then and you don't want to do really experiments, then it's best to use existing data and use the global inverse modeling method. So just take the data from the existing database, from the existing sensors, and take them and rely on heavy analysis rather than the experiments. So in this way, you cannot go really in depth, but then you can compare multiple buildings. So you can look at 100 houses and see if one or two of these houses are performing differently than the others, and then you can go address those houses individually. That's the same as any other industry. Sometimes you don't want the real value, but you just want to identify which one is good and which one is not. So that was it. If you have any questions?
Yeah, I'll ask some questions at the lunch at coffee break, if you don't mind, Hans. We're a bit ahead of that, a bit behind time. Okay. Okay. Stick around for coffee.
Yeah.
That was very good. subject very close to my heart, we'll be able to chat. Okay, so we're gonna move now to our online presentations first. We're gonna take the presentations from the people in the room after those. So first up, we've got Roger Hitchin. So Roger, if you want to put your camera on and your microphone.
Hey, can you hear me?
I can hear you perfectly, Roger. Excellent. Roger,